Hey everybody, let's give this problem a try. So another inductor circuit, and then this switch has been closed for a long time, which means all the current everywhere, whatever is going on over here, 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 they're constant, right? Because the switch has been like that for a while now, which means the current going through the inductor is constant. And then we know that the voltage across an inductor is L di dt. If I is constant, then the time derivative is 0. So then the voltage across the inductor is 0, which means it behaves like a wire, right? Just short like this. So then whatever current is coming this way, all of it goes here and none of it goes here. Okay, so it's like this resistor doesn't even exist, right? Because it's not getting any current. Okay, so basically it looks like this, right? And then I can move this resistor just next to it so it looks nicer. So then now clearly it looks like parallel resistors, and it looks like a current divider now, right? Okay, so how much current is here for the inductor at t equal to 0, approaching from the left? It's a voltage divider, so it is whatever the current here, 30 milliamps, so 0, 3. And then, okay, so this is 9K and this is 1K. So then it's 1K over 9 plus 1. Okay, so 1/10 of 0.03, so 0.003. Okay, so that's the initial current. And then we know that for an inductor, the current cannot change instantaneously. So this is also the current at 0 immediately after we open the switch. Okay, and then after we open the switch, let me change the picture again, then this is all out of there, right? Because we open the switch, and then this resistor is not connected to anything. So basically it just looks like this, where we know the current here is 3 milliamps. Okay, so then let me just draw it over here. All right, so then we got 3 milliamps going this way initially. And we know this resistor. Oh, but we don't know the inductor value. Okay, but then we're given some information, right? So we know that the value, okay, is given, all right? So if I just label the voltage, maybe this way, voltage. Okay, so then the voltage, I mean this current is gonna go kind of going this way, right? So the voltage across that resistor, just the way I label it, right? Plus over here, minus over there, that are going this way. V would be minus IR. Okay, so then that's, I mean, we just plug in the numbers, right? So minus 0.003 amps times 10 ohms would be 0.03 volts. Okay, so we know this is the initial V at 0. Okay, that wasn't the question. We're looking for the inductor value. So what value do we need? Okay, so then V as a function of time is V naught e to the minus R over L t. Okay, and then you can see previous problems I worked out for that. Okay, so we know this, and then we're given this information here. So at t equal 1 millisecond, v at t equal 1 millisecond, I'll just write it like this, e to the minus r over L at 1 millisecond equals 1/2 v naught. Okay, so then you can see how these cancel each other. And then, okay, R is 10 ohms, right? So let me just, can I just write R is 10 ohms? There, okay, so we got e to the minus 0.01 over L equals 1/2. Okay, so we only have one unknown, L. Here's our one unknown. So let's solve for that unknown. We can write kind of like this. Log, and then natural log of E kind of cancel each other out. So you have minus 0.01 over L equals natural log of half. See, there's a minus sign over here. So ln of 1/2 is the same as minus ln of 2. Right, I just wrote it like that so I can get rid of these minus signs. Okay, so that means L equals 0.01 over natural log of 2. All right, so just punch that in the calculator. That's the answer for part A. Okay, and then now we want, what's the stored energy? All right, so we already have an expression for the voltage right here, because now we know the value for L, right? We just got it. And then we know this is minus 0.03. So here we go. We got an expression for voltage. So what is the power? So for the resistor, it's definitely the power is, as a function of time, V squared over R. Okay, let me just square this. So V e to the minus 2r over LT. And then let's not forget the over R. Okay, so this is power as a function of time for the resistor. What is the energy? You just integrate over time, right? Energy is power dt, integral, from 0 to 1 millisecond. From 0 to 1 millisecond. There you go. Okay, so just, right, this goes right there. So just integrate that. Can I just write it? V naught squared over R e to the minus 2r over L t dt. All right, so then just integrate that. Straightforward, I think, right? E to the minus 2r over L t, and then the reciprocal L over 2r. Let's not forget the minus sign. Okay, from 0 to 0.001. Okay, so, I mean, you can clean this up maybe better than me, but V naught squared L over 2r squared. And then there's the minus sign, but how about I just write e to the 0 minus e to the minus 2r over L t, which is 0.001. E to the 0 is 1, right? So can I just write 1? 1. And there you go. Just punch that in the calculator, and that is the energy. Okay, hope that was helpful. See you on the next video.